So as we simplify these, we're looking for perfect squares. The nice thing about the variables is that they're telling us how many we have. Like we know we have 3x's, x to the third. We know we have 2y's, y squared. So with square roots, we're looking for pairs, right? Twos, anything that's divisible by 2. So our 98, if you go all the way to 49, when you make it that far, well, you kind of have to because none of the others go into it, but 49 does. 49 times 2 is 98. So I'm going to break that out as 49 and 2. And then I've got x to the third. Well, this is a square root, so it's got to be something divisible by 2. So I do have an x squared times x. We just broke that up into something with a perfect square, which is x squared. And then we have the y squared, which is a perfect square. So these guys get to come out. Square root of 49 is 7. Square root of x squared is x. And square root of y squared is y. And then what do we have left? We have 2 and an x left under there. So these stay under. These get to come out. Square root of a times square root of b gives me square root of ab. If we're multiplying two fractions, we can multiply them. They don't have to have the same number underneath in order for us to multiply them. But this is also how we can break it up, right? We can break it up into separate square roots. So the product root, or the rule that we have for multiplication with radicals, is just we're doing that in reverse. We can also take products that are there, hidden sometimes, like 49 times 2, and we can just break them up into square root of 49, square root of 2. Questions so far? So whatever the index is, which is the little guy here, this is an index of 3, that tells you you're looking for groups of 3 that in order to come out.
How come the 7xy get to stay out of the radical and the rest of the 2x stay within the radical?
So why did the 2 and the x stay in?
Yeah, the 7x stay on the outside.
Because we took the square root of 49 gave me 7. And then the square root of x squared became x.
So we solved for it in a sense.
So any pairs that we had, right, we can take the square root of these guys and they'll come out. But anything that does not have a pair, so this remaining x still stays inside. And then with the next one, we want to look for groups of 3. It's kind of like they're in jail. If you have a pair, you can get out of jail. But with the number, we want to first find, well, perfect cubes. And there's fewer of those. We have 8, we have 27. By the time you get to, I skipped 4. Oops, didn't mean to do that. 4 cubed is 64. 5 cubed. So by the time we get to 5, we're already at 125. So there's not very many numbers to check with, especially with perfect cubes. And the first one we see that goes into 16 cube-wise is my first one, 8. 8 goes into 16. So I can break this up as the cube root of 8 times 2. I don't have, and 8 is a perfect cube. I don't have enough x's. I only have 2. And I have 3 to come out. So x squared is unfortunately stuck under there. But there are 3 y's in y to the 4th. So we can break that up into y cubed and y. The only 2 that can come out is 8 and y to the 3rd. So the cube root of 8 is 2. Cube root of y cubed is y. And what we have left is 2 x squared and a y. right? So, I mean, I could write several. I can say, okay, well, we have the cube root of 8. We have the cube root of y cubed. These are the two that I took that had groups of 3. And then what was left was 2 and an x squared and 1y. And then this becomes 2. That becomes y. Cube root of 2x squared y. I wish I could take away the little name that trails my pencil, but I can't. Okay, that's the general idea. It takes some practice. And the more you can kind of write, like break it up like this, write them out. You can break them up into separate cube roots, but it kind of gets messy if you do that. So I like to kind of keep it under 1 and then look for those groups of 3 that you have left that you can bring out and then figure out what you have left underneath. Does that make sense? Okay. So the multiplication rule with radicals is as long as they're both the same index, these are both, we'll just put n there. If they're the same index, we can multiply them. So I can't go a square root times a cube root, but I can go any square root times another square root. It's going to be the square root of that product, a times b. However, with addition, we can only add or subtract these if they have the same index and the same number underneath, or same, we call that the radicand. If we have the same stuff, product of numbers or variables underneath, we can add or subtract them, but we're adding and subtracting the coefficients. It's kind of like the same thing we do when we go x plus 2x. So I have 1x plus 2 more x's. That gives me 3x. I'm basically adding the number out front. Because remember what 2x represents. 2x represents x plus x. We're just simplifying it, writing 2x. So literally this is x plus x plus x, like 3x is being added. And so we show that as 3 times x. Multiplication is a quicker form of doing addition. So this represents 4 square roots of 5. This represents 6 square roots of 5. And we have -1 square roots of 5. So these can be combined together. 6 minus, remember that invisible 1 that's there, gives me 5. And then 5 plus 4. So this becomes 5 square roots of 5. And we still have 4 roots of 5. So we can add those, we get 9 square roots of 5. The 9 out front is just telling me how many additions of square root of 5 I have. So these, the way they're written, at least on number 5, we can't add them together. But if we simplify what we have, we might be able to. They just have to have the exact same thing. We call that the radicand. Same thing underneath. So I can't simplify the first one. It's a cube root. I've got a 3 and an x, so nothing can simplify there. But 24 might be able to be simplified. Is there a perfect cube that goes into 24? 8 times 3. So this could be broken up as the cube root of 8. And then we still have the cube root of 3 and x. So I broke that out. This becomes 2 cube root 3x. I still have the 1 cube root out here. So let's write that. This is being subtracted. So we want to keep that going. And with 375, are there any perfect cubes that go into that? 125. Yeah. None of the other ones do, but 125 goes into it 3 times. So, and notice also there's a 3 out here already. So we just want to be careful about that. So we have 3, and then I'm going to multiply it by the cube root of 125. And then what we're left with there is 3 times 125, and then that x that's there. This becomes a 5, so now we have 5 times 3. So that gives me plus 15 3 cube roots of 3x. Now these are all the same. They all have the cube root of 3x, so we can add up these coefficients. There's a 1 there. 1 minus 2 is -1, plus 15 is 14 cube roots of 3x. Cool. So it looks really complicated, but we just have to remember adding and subtracting and multiplication, they're always following different rules. So just be careful with that. As we simplify radicals, we just want to pull out perfect squares and perfect cubes as much as we can. Okay, I forgot my water bottle and my throat's all dry now, which is why I always bring my water bottle. So pardon that. All right, when we rationalize denominators, the reason why we want to do that is if you're doing long division or division without a calculator, it's when you set it up, if you have a decimal here, let's say we have 3.5 going into something here, let's make it 45. We always have to make this into a whole number, the part that's on the bottom. So I actually want to move that decimal one spot. If I do it there, I need to do it here. I'm going to make this 450, and then we take 35 into 450. But when you have a square root or any kind of root that's not a perfect square, those usually repeat forever without a pattern, or sometimes with a pattern. Actually, all radicals will repeat without a pattern. And so there's no way to get this to be whole. So this is kind of one of those older rules that we used before calculators, but it's called rationalizing the denominator. So the general rule is we want to get rid of any radicals that are in the denominator. If I have one, or let's say something, if I just had square root of 2, so 1 over square root of 2, well, with fractions, we can multiply the top and the bottom by a number, and it doesn't change the value because any number divided by itself is equal to 1. So we're just multiplying it by 1. So, and root of 2 times root of 2 is the square root of 4. And so now I have, and on top we still have a root of 2, and that square root of 4 now is a perfect square, so we get 2. So this is the preferred way of writing that. That's the general idea. Now, the problem that I have with the 5 plus square root of 2, if I multiplied this by square root of 2, that would distribute this both here and there. So I'd have the square root of 10. I still have a square root on the denominator. And you can try several different things. Nothing really works except for one thing. And that's what we call the conjugate. You guys remember that word? Yeah. Conjugate is the same thing that's written, but with the opposite operation going on. If I multiply this by the square root of 5 minus the square root of 2, you'll see that this gets rid of, the radicals in the denominator, because this is a addition times a subtraction, an a plus b times an a minus b. And what does a plus b times a minus b give us? The product of a sum and a difference with the same numbers gives us, you guys remember this, a squared minus b squared? Because the inners and outers end up canceling out. When we do this FOIL, we end up with a squared and we end up with b squared. But the AB, that's a positive AB plus a negative AB, cancel out. So we get rid of that middle term that we normally end up with when we use FOIL. We just end up with the square of the two subtracted. And if I can square both of these individually, that gets rid of the square root. So in the denominator now, I have root of 5 squared minus root of 2 squared. So I got rid of the square root down there. Now on top, I have to FOIL this out. Unfortunately, we're not going to get rid of the radical on top. We have root of 5 times root of 5, which is 5. And then we have negative root 2 times negative root 2, which is 2. Negative times negative makes it positive. And then with my inners and outers, we have negative 2 times the square root of 5 and negative 2 times the square root of 5. So that's negative, oops, where's my pencil? There it is. We have minus root 10 minus root 10, which gives me 5. Well, 5 plus 2, let's go ahead and add those together. The numbers can be added. So we have 7 minus 2 roots of 10. And this is all over, this becomes 5 minus 2, so all over 3. You can also break this up as 7/3 minus 2 root 10 thirds. Either one of these is fine. We tend to keep it, unless they want it written as two separate things, we tend to keep it as one fraction. We can keep it as a fraction and simplify it. If 3 went into 2 and 7, then we can pull out a number to cancel with 3. But 3 doesn't go into either of those two numbers. Okay, so that's how we rationalize a denominator if we've got, even if this was a number, if this was just 5, even trying to distribute the root 2 to both of those, that wouldn't work. So if we have a sum or a difference down here, we want to multiply it by the same numbers, but with the opposite operation. It's called the conjugate. Okay, this one employs a bunch of different rules going with exponents, but one thing I want to point out, and the reason why we're even bringing this in, is that when we raise it to a fractional value, the top part is a power, and the bottom part is an index in a radical. So this becomes, well, first of all, and also the negative, you guys remember what happens there, it moves it to a denominator. So, and we have the product of 3 different things. So this can go to all 3. And we multiply that exponent, whatever that is. So 27 to the 2/3. Because I moved it down, that negative now has kind of gone away. And then we have x to the 6th times 2/3. 6 times 2/3. That 3 goes into 6 twice, so we have 2 times 2, so x to the 4th. And then we have 3 times 2/3, which the 3's cancel, so we have y squared. The negative went away because we moved it down to the denominator. And then we distributed that power. Now, 27 to the 2/3 can be written as a radical in 2 different ways. And it's just about the order that you're going to do them in. This is the same as 27 squared and then cube rooted. Or the cube root of 27 squared. It's just about which one you're going to do first. Am I going to raise 27 to the second power and then take the cube root of that? Or take the cube root first and then square that result? Both of them are going to get us to the same place. But if we're wanting to not use our calculators to do that, doing the cube root makes it smaller. So that's kind of preferred. Cube root of 27 is 3, and then 3 squared is 9. So this can simplify one more way as 1 over 9 x to the 4th y to the 2nd. And if you got this one on the first try, give yourself a pat on the back. You remember a lot of different rules all in one. So I want to contrast a couple of things because these are things that trip people up. When we have this group of factors, group of things being multiplied, I didn't want them to go away. This was y to the 3rd. So we had this times, we had 27 times x to the 6th times y to the 3rd. And then they were all raised to the 2/3 power. Anytime we have a product or a quotient, a division, raised to a power, we can take that power and apply it to both parts. And if there's a power within A or B, we multiply those powers together. We want to usually end up, or we tend to want to take a sum or a difference and do the same thing, but we can't. It only works with things that are being multiplied. So this is not equal to a to the m plus or minus b to the m. I call it the do not do this rule. We can't do it if it's a sum or a difference. When we multiply a sum or a difference together, we have to do the whole foiling thing, right? Each part of the sum or difference has to get multiplied by each part of the other. So don't take this rule and overextend it. If you want to point out like the number one thing that people want to do and try to do when they're trying to simplify things is that. So it's good to point out when not to do things. You can know that that's not doable. We can't do that. Any questions over any one of those? This was all your A4. Focus on this because it's a little more difficult. Yeah. Okay, can you speak a little louder? Okay. Which one are you talking about?
For number 6.
For number 6.
I tried doing like, so, because I wasn't sure what you meant when you said rationalize the denominator.
Right.
So I did.
Did you multiply it by root of 5 plus root of 2?
I made it into square root of 10.
Oh.
Is that?
No, you can't do that because
We're
it's
not
being added.
multiplying.
Yeah, if it was times, then that would become square root of 10.
Okay.
Yeah. It's that darn plus sign. Yeah, because that would make it a lot easier. Then you just multiply top to bottom by the square root of 10. And that gets rid of the radical. Yeah. It's not too hard when it's a single radical on the bottom, not being added or multiplied by anything else. If we have like 1 over 2 square root of 3 or something to that effect, the only thing we need to get rid of is the radical. And so I don't need to multiply this by 2 root 3. I just need to multiply it by the square root of 3. And then this becomes a 3, but we also have this times 2, so that would become a 6 down there. If this was 1 over 2 plus square root of 3, we still have to use the conjugate, 2 minus square root of 3. Because if I just do square root of 3, that will put a square root with the 2. And then now we still have a square root in the bottom. So any additions or subtractions, you really have to use the conjugate. And on the top, it's super easy because it's just times 1. So I have 2 minus square root of 3. On the bottom, don't torture yourself by going through the whole FOIL process. Just remember that a plus b times a minus b. So same numbers added and subtracted results in a squared minus b squared. And so that's going to be 2 squared minus square root of 3 squared, which is 4 minus 9, so negative 5. And a lot of times you'll see with the computer, especially, a negative fraction like negative a over b, the negative can be on top or the negative can be on bottom. Oops. They both mean negative AB, A over B. So if you have a negative on the bottom, a lot of times we like to kind of move it to the top. And I think there may be a computer problem or two where if you put this in, it's like they don't like it for some reason. So if we move that negative to the top, making the bottom positive, we just have to distribute that, giving me negative 2 plus square root of 3 instead of having the negative on the bottom. That's another thing that it's not a rule that we have to do that. It's just done a lot. But these are the same thing, with the negative on bottom and the opposite signs on top. Okay. We have 2 assignments to cover. So I want to get to that. Hopefully you spaced yourself out so you weren't all trying to get it done this morning. Remember, you can work past the due date and time. It just takes off 20% for every problem that is done per day in the overtime. So let's go to A4 first. So assuming we're probably going to get most of our questions from that, though maybe not anymore. Oops, let's remove that. All right. Questions from A4 first. Yeah. Number 14. Okay. So notice we have negative 1,000s. Let's just make this big. The negative 1,000 to the negative 5/3. Notice there's no parenthesis around the negative 1,000. This is one of those little things, like negative 2 squared. What is negative 2 squared the way I have it written? It's negative 4. And most of the time you see that, you want to write positive 4 because negative times negative, negative 2 times negative 2 would give us positive 4. But the way it's written, the negative is not being applied to the power. The power only applies to the 2. Exponents only are exponentating, what's that word? Exponating whatever is directly in front of it. We're only raising the 2 to the second power. In fact, You could read this as the opposite of 2 squared, or the negative of 2 times itself, which is -4. So the negative's kind of hanging out, it's unaffected. If we want to square -2 and actually do -2 times -2, we got to put it in parentheses, and then we correctly get +4. So this negative is going to stick around with us. And what this means, a to the m over n is equal to either the nth root of a raised to the m power, or a to the m power nth rooted. Just about, again, which one you're doing first. To do it in your head, it's usually easier to just do the cube root first. This is going to be the negative cube root, if we were to translate it into radical form, cube root of 1,000 raised to the -5th power. We can deal with the negative by simply writing this under 1. So it's 1 over, and now we can make that positive. A to the minus m is equal to 1 over a to the positive m. Let me talk about that just to remind you why that is. It seems like such a weird rule. Like, why in the world would this become 1 over because it's negative? Like, the negative power actually has nothing to do with it being positive or negative. But if you look at the pattern that happens, like if you have 2 to the third, that's 8. 2 to the second is 4. 2 to the first is 2. What's 2 to the 0? 1. Anything to the 0 powers is 1. Notice that I'm dividing by 2 each time. And so when we continue that pattern, go 2 to the -1, this is 1 divided by 2, which is 1/2. 2 to the -4 is 1 over 2 squared, or 1/4, 1/2 divided by a half, or divided by 2, or times 1/2. So it is the pattern just continue. So that's why it does that. What is the cube root of 1,000? Cube root of 1,000, 10, right? So this is 1 over 10 to the 5th power. And we still have that negative here, which is 1 over 1 with 5 zeros. So 1 over 100,000, and it's negative. Negative because, well, this was out here to begin with. Oops, and I want to put the negative. You can either put it out front, or I think if you put it on top or bottom, it'll. Let's see if we put it on bottom, if it would accept that. I think it will. Yes, it should. Does that make sense? That answer your question. Was it the negative? Yeah. Normally, well, even if we raised it to an odd power, it would stay negative. Stuck with that there. But yeah. Any other ones? Going once? I know there's other questions out there. Number 10. Okay, yeah. Those are some fun numbers. So we may need to go a little higher in our cube root search. We know we had 2 cubed was 8, 3 cubed is 27, 4 cubed is 64, 5 cubed is 125, 6 cubed 36 times 6 is 216. You're getting kind of close to those numbers. 7 cubed 343. Yeah, let's try 8 cubed. It's 512. So I'm going to stop there because I know 512 times 2 is bigger than my largest number there. So we don't have any perfect cubes in either of these, but there may be smaller ones. So let's start with 448. It's 448 divisible by 8. It is 56 times. So 448 is 3 times 56. Is that right? No. What did I do? Oh, I divided by 8. Is 8 times 56. Is there another perfect cube in 56? 8 times 7 is 56. Right, so there's 2 cube roots here, and 8 times 8 is 64. So 64 is actually 64 should go into 448. So a better way to break this up, 448 is 64 times 7, because 64 is a perfect cube. Cube root of 64, cube root of 7, cube root of 64 is 4. So 4 square roots of 7 is how the cube root of 448 can be broken down to. No. So 4 square root. What the heck is going on? 4 square roots of 7. What about 875? I suspect that 7 goes into 875. Why? Because I'm suspecting that I'm going to be left with another 7. Now, I don't know if it does. 875 divided by 7 is 125. So this can be broke up into the cube root of 125 and cube root of 7, leaving me with 5 square roots of 7. Why did I suspect this? Because this is an artificial problem that they've created, and they're probably going to make me want to add those together once I simplify them. So more likely than not, they're going to give me the same thing left over underneath the square root. And then when I add that together, I get -1, so negative square root of 7. But we had to find those square roots, and in this case, it was a cube root of 64, cube root of 7, and these are cube roots. Don't forget that. You can see I get sloppy sometimes as I'm going through. I forget to put that cube in there. So don't do that. That's 3 and 7. Let's see if we get our positive affirmation there. Right. It's just some bigger numbers. If you're doing cube roots, they're probably going to do that to you once in a while because there's not a lot of cube roots. By the time we get to 4, we're already at 64. If you want to do it by hand, you can always just break it down by prime factors. Just these are going to give you big trees. So 448, we know that's 2 times 224. And then stick with 2 until you can't use 2 anymore. 112, 2 times 64, 2 times 32. You keep using 2 till you can't, then go to the next prime number, which would be 3. 16. I screw up somewhere along here. 64, 32, 2 times 8. How am I getting all 2s? 28. 224. 212. Oh, that's where I screwed up. 112 divided by 2 is 56, not 64. And then 56 divided by 2, that's 28. 14, and then 2 times 7. So then you're looking for groups of 2. So I say use 2 so you can't use it anymore. Otherwise, it'll get kind of lost. And then you look for groups of 2. The cube root of these 3 becomes a 2. Cube root of these 3 becomes a 2. And then we're left with the 7. So 4 square root of 7. That's the way you can do it by hand. Any others? From A4. 17. Shit, damn brakes. Aha. 4u to the 4th to the 3 halves. 4u to the 4th. 3 halves, you may have different numbers. That's okay. We know what a to the n is. Just remember that when we divide it by something, that's the new part. Like the top part is always the power. The bottom part is kind of the new. A to the m, we could write as m over 1 because anything can be written over 1. We just don't do that. So the denominator part is the new part. And it's the opposite of power, which is a radical because we're dividing it. So it's the opposite of power. Like a to the 4 over 2 is the same as a squared. Well, the square root of a to the 4th is a squared. So it does the same thing as a square root. It cuts that exponent in half, which is what we do with the radical. You can always take these and divide it by the index. Okay, so this is 4 to the 3 halves. Don't forget about the number. And then u to the 4 times 3 over 2. This is 4 over 1 times 3 over 2. So the u is going to become 2 goes into 4 twice, so 2 times 3, so u to the 6th. We're basically just multiplying those exponents. A to the m raised to the n power is a to the n times n. We multiply those exponents. This 4 has a 1 there. So that's 3 halves times 1, which is 3 halves, and then 3 halves times 4, which is 6. That denominator of 2 is a square root. So another way to write this is the square root of 4 to the 3rd power. Kind of helps to write it out that way, like turn it into a radical. And I like generally will tend to do the root first because it makes it a smaller number. The square root of 4 is 2, and I know what 2 to the third is. It's 8. But I might not know what 4 to the third is, right? That's 16. It's outside of our multiplication tables. But I do know that the square root of 4 is 2, and I know that 2 to the third is 8. So this gives me 8u to the 6. So 3 different rules that we're applying there. We're applying the fractional power rule, fraction power rule, doing a product to a power rule. So we're doing two things in a parenthesis that are both being raised to the power. So we multiply those exponents. Remember that 4 does have a power there. It's just not written. It's a 1. So we are taking the 3/2 of the 4 as well. What people tend to do is forget about the number. They skip over the number. It's common. We all kind of do it. Next one. Going once. Going twice. Okay. Let's go to the next part here. Which is the review of lines. Hopefully this was a little more like in your memory. Slope, x-intercepts, y-intercepts. Questions from this one? $14. Start with 14. Write an equation in slope-intercept form of a line satisfying the given conditions. The line passes through -2, 2, and is perpendicular to the line whose equation is x equals -5. All right. Let's make that a little bigger so you can see it. So typically, I mean, equations of lines can take on a bunch of different forms. We have standard form, ax plus by equal to c. This is the standard form of a linear equation. The main thing about a linear equation that makes it linear is both x and y are both being raised to the first power. Slope-intercept form is the most common because it's solved for y. So we like our final answer a lot of times to be solved for y equals mx plus b, where m is our slope, b is the y-intercept. We also have the point slope form. This is the lesser known one of a linear equation. This is more of a formula, but it's useful when we know a point the equation is passing through and the slope of the line. Y minus y1 equal to m times minus x1, where x1, y1 is a point on the line and m is a slope. Well, m is always a slope. You guys know that. So if we know a point and a slope that it passes through, well, we can use that one. But this one is a little easier because they say that x is equal to -5 is the equation of the line that it's perpendicular to. X equal to -5. 1, 2, 3, 4, 5. This is where x is equal to -5, but it's not just there. X is equal to -5 all along here. This would be -5, 1. This would be -5, 2. This would be -5, 3. So this is the place where x is equal to -5. In 2 dimensions, it's a vertical line. What is the slope of a vertical line? Undefined. It's kind of an infinite slope. Slope is the change of y as we change horizontally. So how far we're going up vertically or up and down, divided by how far we're going to the left and to the right. And since we're not going to the left or right, we're just going up or down for eternity. We say there is no quote unquote slope. But a slope of a horizontal line, that's what has a slope of 0. So if it's perpendicular to this, we know it is a horizontal line where the slope is 0. So here there's no change of x, so we have something over 0. This is when it's undefined. If there's no change on x, there's a 0 change of x, we have undefined. But if we have no change in y or no change in my height divided by some number, this is a 0 slope. And these two mean totally different things. So if you're ever writing 0 with a line through it, if you've been in the military, I know they kind of do that with all the zeros. Forget that, because if you do that, you're telling me it's undefined. 0, that's just 0, should just have a 0 there. So I know it's going to be a horizontal line, horizontal line. It's going to pass through -2, 2. Then it has to be this. That's passing through -2 with a height of 2. This is a y equals 2 line. Now, if we use the slope intercept, if we know that the slope is 0, 0x plus b. And we substitute this point to -2. That would give me 0 times 2, which is 0, plus b equals -2. So that tells me that b is -2. The y-intercept is -2. So in the slope-intercept formula, with the slope being 0, x plus -2, that cancels out, and I'm left with the equation y equals -2. So we can have a slope of 0, which says that we're not rising no matter how far we go. We're still at the same height.
Is it 2 or negative?
What did I put? I put -2, right? I might have to use the negative button.
And then the line is 2.
Oh, I'm sorry. I put 2 in there, but it should be 2. Y equal 2. Yeah, thank you. Let's see. My x was -2. My y was +2. Thank you. So 3 standard form, slope intercept, just know what those are. Any other one of these where we do a perpendicular where it's not a weird situation. Let's look at this one. Find the slope in the intercepts. And then, that's not the one I wanted. Looking for the parallel perpendicular. Okay, here's one. So if two lines are parallel, what do we know about their slopes? Two parallel lines and their slopes, they're the same. They're going up and moving to the left or right, same speed. So parallel lines have similar slopes. If this is the slope of this is the slope of that. They are equal to each other. But if they meet perpendicularly, this is M1, the M2, well, we don't want, let's pretend they're not horizontal, vertical like that, but M2 will be 1 over M1, the reciprocal of M1 with the opposite sign. So we say the negative reciprocal. So if I have, let's see, we have these two equations, x equals 6y plus 16, and y equals negative 6x plus 3. Well, there's a couple ways we can figure out the slope of each. This one is in slope-intercept form. So I know that the slope here, we'll call it M2, is negative 6. It's the value, the coefficient of x. This one is not in any of our forms. I can solve this for y, and that's one quick way to find the slope. I can also put it into, this is the lesser known way, standard form where x and y are on the same side. I'm just pointing this out because it's a handy trick to have. If we have ax plus by, if it's in standard form, the slope is the opposite of a divided by b. So if I subtract 6x to the other side, or 6y to the other side, I end up with x minus 6y equals 16. This is now in standard form. And so if I take the opposite of a, that negative here means negate whatever a is. So a is a positive 1. I'm going to take negative 1 over the value of b. So negative 6. That's 1/6. This is my M1. So I have 1/6 and negative 6. That tells me if I take 1/6 and I find its opposite reciprocal, it's going to be 6 over 1. It's a reciprocal, and then negative. And look, that's the slope of the other line. That tells me these two lines are perpendicular. If this was negative 1/6 and then we had negative 6 here, they're not parallel, they're not perpendicular, they're neither. So sometimes it's going to be neither. Be aware of that. But all we need to do to find the equation of a line is a point it passes through and its slope. Those are the two things we need to find the equation of a line always. And I want to go over that process. I was hoping one of those would come up here. That was going to be one of the questions I was going to put on your 15-minute check too, but it just got so long. I figured, well, this will come up during the discussion. Here we go. That's a horizontal line. That's a vertical line. All right, let's okay, here we go. Just want to go over this. Finding the equation of a line. Here we're told that we want to find the equation of a line that's perpendicular to negative 1/4 and passes through negative 5 or negative 3, 5. So if it's perpendicular, what is the slope of the line that I'm after? If the slope it's perpendicular to is negative 1/4. 4. Right? Opposite sign, flip. Negative, when we refer to like negative, we're talking about the sign, the opposite sign. So the negative of the reciprocal, the opposite sign, reciprocal. Reciprocal means flip it, so that would be 4/1. So the slope of this line is going to be 4, and we know it passes through this point. There's a couple ways to do this, and everybody's kind of been taught differently. So I'll do both. All we need is a slope and a point it passes through. If we're given 2 points, we can figure out the slope. Difference of the y's divided by the difference of the x's. But here we're given the slope. And so if you use the slope-intercept form, y equals mx plus b, this is probably the way most of you have been taught. We have part of what we're after. We want the y-intercept, and then we want the slope. So let's go ahead and put that slope in there. Now the only thing we have left is the y-intercept. But we have 3 different variables. So I can temporarily use this point I know it passes through, -3 for x and 5 for y, to get rid of the other 2 variables, which just leaves me with b, which is what I need in order to have this equation. So it's kind of a temporary thing we're doing. We're just we're putting in 5 and -3 for y and x respectively, for the purposes of figuring out b. That gives me -12 plus b equals 5. So I just took out my x, took out my y. And then we add 12 to the other side, which gives us 17. So that's my equation. Y equals 4x plus 17. So that's probably the way you've learned it. The other way is to use the point slope form of the linear line, that other formula I pointed out earlier, which is just as its name suggests, revealing of a point and a slope. So point slope form. It's more of a formula. Y minus y1 equals m times x minus x1. Again, a formula that has subtractions in it. Be careful. X1, Y1 is a point that it passes through, and then we want the slope there. So if I substitute that in, y minus blank equals blank times x minus blank. This is one way to keep yourself from making that mistake of not plugging in a negative, but you think you are. For the x, especially because it's negative, if you write it out with the blank spot and then just put those numbers in there, we have 4 for our slope, -3, and then 5. So notice how I avoided the mistake of writing x minus 3, thinking I'd plugged in -3, because it actually becomes plus +3. And distributing the 4, that gives me 4x plus 12. You still have y minus 5, but all I have to do now is add 5 to both sides. That puts it in slope-intercept form. Most of the time, they're going to want it in slope-intercept form. Same equation. In fact, once you have these points in there, that is the equation of the line. There's only an x and a y left. It's just in this weird form that doesn't tell us a whole lot. I mean, it does tell us a point it passes through, and it tells us what the slope is. But it's just, it's kind of messy. Our numbers aren't combined together. It's not messy. So we either tend to leave these in standard form or slope-intercept form. How many of you typically do these this way, first way? So that's the way you were taught. How many were taught using the point slope form? Oh, okay. Wow. I thought this first one was the more commonly used one, but for whatever reason, it's the one math teachers like better. I actually like this one. To me, it's more straightforward. Okay, any others from your homework? Yeah, on one of the lectures. X squared.
I'm sorry, it's 8 squared cubed.
Oh, 8 squared and then cube rooted. Okay. And it just said simplify this. Oh, okay. Was it -8 or was it just 8? Okay. So that whole plus and minus thing comes about. Well, first of all, it's a cube root, so we don't worry about that with the cube roots or any odd root. But if we're presented with, like they say, simplify this, they didn't write a negative out front, so we're doing it specifically for a positive cube root of 8 squared. That whole plus and minus thing comes about when we're solving equations. This equation, for example, says what number squared will result in 4? And you can tell by the power of your equation how many solutions there are. Now, in general, sometimes those solutions are imaginary, okay? But let's just set that aside. As a general rule, the power tells you how many solutions there are, because 2 is not the only number that if we square it gives us 4. -2 also, if we square it, gives us 4, right? But in the process of solving this, one of the things that we do is we say, well, let's do the opposite of square it. Let's take the square root of it. Well, what happens when we take the square root is it takes it down to a 1x to the 1. So a 1 degree equation, which should only have one solution. And so to keep the other solution in play, when we take the square root of both sides, we always want to put a plus and minus out here so that we're getting both of those solutions that exist in the 2 degree equation. Yeah. So that's the only time I have to worry about it. If this is just presented like this and they don't put a negative out there, you're only dealing with the positive, not the negative. And so whatever the answer is, it's going to be, well, in this case, a couple ways you could do this. I just want to point out 8 as 4 or 2 cubed. So you could say, well, this is 2 cubed, but remember that 2 cubed, rewriting 8, is being raised to the second power. And then we're taking the cube root of it. So that's 2 to the 3 times 2 to the 6th power. And then there are 2 groups of 3 2s there. In fact, you can see that here. There are 2 groups of 3 2s. And so, or when you're taking the root, you're really taking the 2 exponents and dividing them. This is 2 to the 6 over 3, right? 3 being the index, 6 being the power. So that reduces down to 2 squared or 4. But the reason we don't take -4 as well is because there's no negative written out front. Great questions. Okay. I do like to save the last little bit of class for, well, either group work or people having questions and they need me to do things before the other class comes in. So if there's no other questions from here, I do want to leave some more time if there are more questions from the homework assignment. All right, there's only one section we have to cover for Wednesday, and that's the 1.4. So that's what you'll be working on from now until then. Remember, you can work off the after the due date and time. Just going to take 20% off for any question that was done in the overtime. Have a great couple days. We'll see you on Wednesday.